Welcome to today's Zurich Instruments webinar. My name is Jelena Trbovic, and today with Heidi Potts, we're going to talk about the interfaces and how they make or break a nano device. We're application scientists here at Zurich Instruments, company founded in 2008. We now more than 100 people, and we have offices all around the world, including USA, China, Italy, Korea, France, Japan, and Germany. And since last year, we are part of a bigger Rohde & Schwarz family, and together from now on, we will continue working on our products, mainly lock-in amplifiers that we started developing early on, that work in a broad frequency range up to 600 megahertz, but also working on quantum computing control electronics like AWGs or qubit analyzers, as well as quantum computing control systems that work up to 8 gigahertz. So let's see how today's webinar will be structured. So Heidi and I will divide it in two. In the first part, I will talk about the interfaces, the basics, and how to characterize them using lock-in amplifiers. Then we're going to make a short break to answer some of your questions that you might have. If you could put in the questions box, we'd be happy to pick them up and answer them mid-webinar, and then Heidi will continue talking about quantum dot characterization in transport and RF reflectometry, and we will wrap up with final set of questions. And of course, if we don't get to answer all your questions, we'll get back to you. We'll also write a blog about it. Okay. So let's get started. So there are many reasons that we want to study interfaces and understand their role in nano devices. Here I show a FinFET, IBM's 2 nanometer chip devices that we see that they're perfected to down to sub-nanometer level. And in order to make this huge chip work, everything really needs to be nicely done, and the interfaces have to be perfect. Of course, when we move to more novel devices, when we combine different materials and different nanowires here, for example, we see that in order to understand how they function, we can basically look at these 3 types and characterize each of these interfaces, which are set up differently. So let's get a few steps back and to understand why we even want to contact and make these interfaces. So first of all, we want to characterize the materials, and in order to do that, we need to put some metallic leads onto the material, and depending on what type of material we contact, we will have either an ohmic contact or a Schottky barrier. Maybe we want to put a tunneling barrier. But in all cases, we need to understand what these in particular are so we can extract the proper material characteristics. Furthermore, what we want to do, we want to be able to use some electrostatic gating to control, for example, semiconducting properties where the gate's efficiency is going to play a major role, so we know exactly what each gate step will do to a device. And of course, as I mentioned, hybrid devices, we want to combine different quantum mechanical properties from superconductors or magnetic materials to use the spin and make sure that all these components work together in a single device. Now, when we reduce the device size, what really happens, we actually start being aware of the details of the interfaces. They actually play now a major role, as you see here. So every single impurity, the roughness at the interface will also be a part of the device. Another thing that happens at low scales is that we start seeing quantum signatures of quantum transport. We will have a finite number of conductance channels, and each of them will have a quantum conductance, 2e squared over h, and will be associated with the transmission coefficient, which will in effect give you the information about the interface. And of course, in all these, so this is given by this formula over here, very simple, and of course the same concept will apply to when we want to control them or we want to use these quantum channels to give them a different flavor with superconductivity or spin, for example. Another important aspect that we need to have in mind when we want to characterize these devices and their interfaces is that the energy scales need to be set and understood. So everything that we do in our experiment basically does not interfere with main device characteristics. So for example, for a quantum dot, we have a level spacing on the order of milli-electron volts, and basically we want to make sure that every excitation that we apply is smaller than this particular value, so we don't smear them out. And of course, when it comes to superconductors, the superconducting energy gap is the one that sets the stage for the energy considerations, and of course, the temperatures where we keep these devices and all the energies need to be, again, much smaller than the given energy scales. And what does it mean when we actually come to a device that we want to study? So on the table here on the side, you can see how temperature converts into the photon energy or the voltage from a probing device. So you can see these levels. And of course, we know that in order to reach low temperatures, we need to cool down our samples in the cryostat. Then the photons can be either controlled via a microwave signal generator, or we need to shield the cryostat so these types of energies don't interfere with the experiment. And of course, the instrumentation needs to be such that it provides the high energy resolution of the voltage that we applied, for example, to be low noise, in order to be able to extract the physical properties that we are interested in. So the best way to do that when it comes to measurement is actually to, first of all, understand the noise environment. So we measure one of these the frequency spectrum of the noise, and of course we are looking at our physical system. We need to choose where is it that we want to do the measurement, and of course the most important thing is to make sure that the signal to noise ratio is the highest. So we want to avoid the noise, and we also want to modulate the signal in order to choose the best spot for our measurement. And for that, lock-in amplifiers are really one of the best solutions to do that. So let's see how they work. So first of all, to see what they actually measure. So what they measure is the amplitude and the phase of the signal that's been sent into the physical system through a reference signal, and then it comes back at the input together with the noise. And if we want to then extract the amplitude and phase, this is done in a process called demodulation. So if we have a signal and the reference expressed like this, like a sine wave for the signal and a cosine for the reference, we then start mixing these two signals, and mixing means multiplying them. And in order to extract the amplitude and the phase information, there are two things at least that need to happen. First of all is that the signal and the reference are at the identical frequencies, and that we make two products, one in and one out of phase with respect to reference. So we get these two terms. Just a second. So we get these two terms. One is time independent, and this one here is time dependent, contains the 2 omega component. And basically what we want to do in the next step is we want to use the filters in order to get rid of the 2 omega components and the noise that comes together with the signal. So at the end, we then get the two equations, x and y, that contain the amplitude and the phase. Okay, so now if we start from a very simple example, we have two metallic contacts that we put together. Their Fermi energies are aligned, and we hook our device up with the lock-in amplifier, so we can basically output a probe signal over here, say voltage, and measure the upcoming current on the other side. And what happens when we apply the DC bias basically is we shift the Fermi energy of one of the metal leads, and we get this really nice linear term, which tells us that these two metals have nice atomic contact. But if there are states at the interface or a barrier, we will see the deviation from this curve, and it's best to do that by applying a modulation on top of this DC signal, or in fact get the lock-in amplifier response, which in the case of the linear response of the ohmic contact means just a flat dI/dV, so the first derivative of this curve. So now what happens if we put a superconductor on the other side and say we have some sort of barrier in between? So first thing that we note, of course, metallic materials have single particles, electrons that carry the current, and on the other side there are Cooper pairs that carry the current in the superconductor. So now these two need to match, and depending on the transparency of these barriers, there are several things that can happen. So if the barrier is not transparent, what will happen is that the electrons will bounce off below the energy gap of the superconductor, and in effect you will not see any current. You will not see any current in the subgap region, and then when you pass this energy, you will again start seeing the current. And over here you can see the dI/dV characteristics of this tunneling contact. And now as the transparency actually goes up, we see that we start seeing the current in the subgap, and again a lift off of this dI/dV curve. And now finally, if we have contacts which are completely transparent, we can start seeing the Andreev reflection coming in, which means that in order for the Cooper pairs to go forward in the superconductor, an electron in the normal metal needs to pair up with a hole with the opposite spin and the opposite momentum in order to keep the charge and spin conserved. So we have an ivory characteristic like this, and the dI/dV basically shows that we have the doubling of the conductance due to the Andreev reflection on this side. Okay, so let's see a couple of examples. So first of all, what I'd like to show you is how a quality of the contact actually influences. You can see it in the dI/dV curve. So in this work, the group has shown how evaporated contact, either directly aluminum or titanium with aluminum on top. You can see the device over here. You can see the device over here, and the curve that's been measured has gotten something like this. And you see how this subgap region is lifted up. And in fact, this is very soft gap due to the interface properties. And when epitaxially grown aluminum is then put on this indium arsenide nanowire, we can then see how the subgap region becomes much deeper. And what this really means is that you can see the subgap processes, which are important as for operation of the device. Now we also know that if we now that we have a semiconductor, that we put a gate on the side, this is also done using the lock-in amplifier, we can both gate and change the electronic properties of the semiconductor, but also we can directly influence the transparency of these gates, of the tunneling barriers. So this is one example where actually quantum point contact in this aluminum indium arsenide interface over here, QPC over here has been gated in order to change its transparency, and over here you can see how, as a function of gate, the transparency changes. So this is in a very lower region over here with low transparency. And if we go a little bit higher up, we see still a hard gap, but higher, a little bit higher conductance for this particular work. Furthermore, what's really interesting in another work from Morten Kjærgaard is again when we have epitaxially grown aluminum on top of indium gallium arsenide barrier and indium arsenide in between. We actually see how by tuning the gate voltage we can go from the doubling of the conductance as I shown already for Andreev reflection. So this happens in this highly transparent region, and over here when we go into the more closed region, we see a tunneling curve with a lower transparency of this quantum channel. And finally, what I wanted to show is another is a work also done with Mfli. Is again now a contact between a superconductor, indium arsenide nanowire, and superconductor. In that case, we will have in the case of an open transparent barrier, we will see the signatures of the supercurrent that you can see over here. And over here in this region of a closed barrier, we see tunneling. This is a little bit more complicated a picture, which we'll not go into, but nevertheless, this is an example how you can tune the transparency of the contact in the whole region. Okay, so to summarize this part of the presentation. So what we have seen is that interfaces are indeed extremely important, first of all, to be made properly and to understand how they influence the device properties, how we can make sure that by doing the IV characteristics and differential conductance measurement using the lock-in amplifier, we can really see all the subgap features if we have a device which has low noise, high resolution, and also high speed helps in performing these longer measurements. So this is what it takes to do them. So this is now the end of my presentation. So we will now have Heidi take over.
Yeah, thanks a lot, Jelena, for this overview of how interfaces play an important role for nano devices. Now this is the time to ask a couple of questions to Jelena. So if you haven't done so already, please use the questions box here to type them in, and we will ask them. So we already have a few questions. Jelena, you mentioned that the contacts can be of different quality. Is it possible to do 4-point measurements with the lock-in amplifier?
Yes. Thanks, Heidi. That's indeed possible. So if I just go back a few slides, that's indeed possible. When I show this in a very simplified two-terminal, okay, this is already three-terminal geometry with a gate, but in this two-terminal measurement of the conductance, we basically have a DC bias applied and an AC excitation, and we measure the current here. And of course, we can, with Mfli, we can use these differential voltage inputs as well to, in more complicated structures where we have additional ports to actually measure four terminal at the same time.
Okay.
So this is indeed possible.
Okay, that's good to know. Then there is another question. You mentioned that we modulate to get away from the noise. Can a lock-in provide this modulation?
Yes, lock-in is a device that actually provides this modulation. So in principle, MFLI can go from DC to 500 kilohertz and 5 megahertz, so you can choose this in your device. So that is correct, yes.
Okay, and that connects very well to another question that we got. It's, can you also measure DC voltages and currents using the lock-in?
Yes. So MFLI in particular is actually the only lock-in that can measure DC and AC at the same time with some small changes in the software. So it's very simple. You really just need to type 0 instead of any frequency, and you will be able to demodulate with the same process and get voltage or current in some cases if you want, or you can also get both current and voltage.
Okay, and then there's a final question. Is there a rule of thumb regarding the lock-in low-pass filter bandwidth? How can I set it up?
Yes, so basically what you can do is to be on the safe side. Let's say to have definitely, if you want a rule of thumb, maybe 10 times you divide your frequency by 10. So for example, if you measure at 100 hertz, you can have maximum 10 hertz bandwidth. And lower, of course, you need to be careful not to pick up the 2 omega component, and maybe in that case you will have much more noise. So I think Heidi will show a little bit later how you can actually see how much noise you have, whether you have the 2 omega component. So you can set your measurements properly, but maybe start off with some 10 times a factor of 10 for the frequency, or if you know the time constant, you can also start off with that and convert into bandwidth.
Thanks, Jelena. Actually, there's one more very quick question. How many measurement channels does the MFLI has?
Mm-hmm. Okay, it's a quick question. There is a little bit of things we need to count. So basically, there is a current port. It's a separate current port. There's also differential voltage inputs. You can use it differentially or single-ended. And then you have auxiliary input over here that in case of MFLI with the so-called multi-demodulator option, you can use these as well to demodulate voltage signals as well. And at least, so I would say at least 4, but there are different ways you can measure even more.
Okay, thanks a lot. So there's more questions coming, but I think in the interest of time, we will continue with the second part now, and then maybe we can have some questions for Jelena at the end. Right, so now in the second part of the webinar, we will talk about quantum dots and how to characterize them. And in particular, I will show 2 examples. I will show how to set up a low frequency transport measurement as well as an RF reflectometry measurement. And I will start by explaining why interfaces are so important for these devices. So a quantum dot is a small island where charge carriers are confined. They have been widely studied since many decades, often for fundamental questions, but more recently also because a single charge carrier with a well-defined spin can be used as a quantum bit for quantum computation. So schematically, a quantum dot device looks as shown here. So here's our quantum dot, and this can be connected to a source and a drain contact via 2 tunnel barriers. And in addition, you typically have at least one electrostatic gate, which is shown here, that allows you to change the potential of the quantum dot. Now, if you want to draw an energy diagram, it looks like this. So here you can see the chemical potential of the source and drain contacts. you can see the two tunnel barriers. And then because of the confinement, you have discrete energy levels on the quantum dot. And as Jelena already said, this spacing of these energy levels is typically on the order of a few milli-electron volts. Now, it depends on the alignment of the different potentials here, whether or not it is possible to have current flowing through the device. So in this configuration, for example, it is not possible because none of these energy levels from the quantum dot are available within the bias window of source and drain. But now we can use the gate voltage and the source drain bias voltage to change the potential of these individual components. And so we can reach configurations like this one here, where it is indeed possible for a charge carrier to tunnel onto the quantum dot and then out to the other side. And of course, we can further increase the gate voltage. In this case, we would pull down the quantum dot levels. And in this scenario now, you can see that there are two electrons that are denoted by the arrows here for the spin, are sitting on the quantum dot. But in this case, once again, it is not possible to have current through the device. We're in the Coulomb blockade regime. So overall, if you want to characterize a quantum dot device, you typically record these two-dimensional diagrams where you record the conductance through the device as a function of gate voltage and source drain bias voltage. And then you're expecting to see these very characteristic Coulomb diamond structures where you can identify that inside these diamonds here, the charge on the quantum dot is fixed and no transport is possible. And inside these regions here, it is possible for charge carriers to flow through the device. Of course, the charge carriers can be either electrons or holes, depending on the material that you're using. So to make such a quantum dot device, you typically start with a already low-dimensional material, such as a two-dimensional electron gas or a one-dimensional nanowire. And then you additionally confine the charge carriers into 0 dimensions using additional potential barriers. So here are a few examples. In this example here, two quantum dots were defined using electrostatic gates that you can see here on a two-dimensional electron gas. And in this example here, there's a nanowire, so already a one-dimensional structure, and then the additional potential barriers are created using bottom gates. And in both these examples, it is of course very important that the interface between the gates and the material itself are of high quality in order to ensure that you have a well-defined potential profile. Here at the bottom, you see a slightly different approach. In this case, the quantum dots are defined by changes of the material composition or the crystal structure. So let's look at these examples in more detail. This here is a transmission electron micrograph of an indium arsenide nanowire. And during the growth of this nanowire, two very thin indium phosphide sections have been inserted. They're shown here in dark in the TM image. Because of the difference in electronic properties of these materials, now these sections will act as potential barriers and essentially confine the electrons in this segment here. So this will be our quantum dot. On the right here, you can see a somewhat similar approach. In this case, it's also an indium arsenide nanowire, but the potential barriers here were created by changes in the crystal structure. So the crystal structure of this indium arsenide nanowire is mostly zinc blende, but now two sections of word-side crystal structure have been inserted, and there's a small zinc blende section in between. And now also these crystal faces have a different electronic properties. And so it turns out that the electrons will now be confined in the central zinc blende element, which is a quantum dot. Now, as you can see from the reference, this topic is actually very close to my heart because I had the opportunity to study such quantum dot devices as a postdoc in Lund. So to sum up, we've seen that interfaces are really important when you want to make quantum dot devices. However, they can also completely destroy your device properties. And so here on the right, I'm showing another TM image as an example, where you can see that the stacking sequence, so the crystal structure, changes somewhat randomly. There are a lot of interfaces within this nanowire. And what will happen now is that charge carriers will be trapped in very small islands, which are impossible to control individually. So for the device properties, this essentially means that you just observe some random scattering or noise. Let's continue with some measurement considerations. So if you want to measure such a device, you of course have to fabricate the contacts. Here at the bottom, you can see an SEM image of such a device. It's based on a nanowire, and then there's a source and drain contact and 2 gates. And because of the small dimensions, so here you see the scale bar, it's 500 nanometers. Typically, you make these contacts using electron beam lithography, followed by metal deposition and then lift off. As a next step, you then have to choose the right measurement environment. And as Jelena already said, this is very important because the quantum dot levels, like the energy spacing between the different levels, is on the order of milli-electron volts. And so you have to cool down the device to be able to resolve these individual levels. You can do this either using liquid helium, so this brings you down to 4 Kelvin, or you put your sample in a dilution fridge as shown here. And finally, you have to choose the right measurement electronics in order to be able to precisely measure the properties of your device. So this can be done using DC measurements, lock-in measurements, or RF measurements, as I will explain now. First, here's a somewhat more realistic example of such a measurement setup, how it could look in your lab. So this is a dewar that can be filled with liquid helium, and then you immerse your sample inside this helium bath here. And to do this, you would mount your sample onto a long rod here that is called a dipstick. And then you have the electrical connections with wire bonds to some small shielded wires that go outside of the dewar to a switch box. And from that switch box, you can then connect your measurement instrument. And with this, you would be all set to start measuring your quantum dot device. So what you typically start with is to apply a small source drain bias voltage and then record the conductance as a function of gate voltage. And you're expecting to see this kind of transistor-like behavior, where in this case, the conductance increases as when you increase the gate voltage, so it's an N-type device. Now, the region of interest here is here close to pinch off of the device. This is where you will be able to see the individual quantum dot levels. So you would then zoom into that region and do a next measurement, and then you should be able to observe these individual conductance peaks due to transport through the individual quantum dot levels. And then you're all set. You can map out the full Coulomb-Diamond stability diagram that I've shown before by sweeping the source drain voltage and the gate voltage and measuring the conductance. In terms of measurement electronics, Jelena has already introduced it. Such a quantum dot measurement can actually be entirely done with the MFLI lock-in amplifier. So here's our device under test. It would be our quantum dot device, and we can apply a voltage to it and then measure the current. In this case, we would use a voltage that consists of a DC component and then a small AC component for the lock-in measurement. And then with the lock-in measurement, you can directly get the conductance as the ratio between the AC current and the AC voltage. Additionally, we have these 4 auxiliary channels here on the right that allow you to apply static or more static voltages, for example, the DC voltages that you would use to control the gate of the device. Now, I would like to show you a quick pre-recorded demo of how to set up such a measurement. So here you can see the user interface of the Mfli lock-in amplifier. On the top, you can see where the lock-in amplifier can be controlled, as well as the output voltage. And here on the bottom, you can see the built-in oscilloscope function that you can use simultaneously during the measurement to directly monitor your input signal, such as the current. So let's get started. We start by creating a test signal. We choose a frequency here of 314 Hertz. Choose the amplitude here, 10 millivolts, and then apply this to our device under test. And then we use the oscilloscope function to monitor the signal, and we can nicely see that the current oscillates as expected. Now, for the measurement, we are interested in the precise measurement of the amplitude and the phase. And so here you can see the numeric values, and we can see they're actually oscillating quite a bit. So we want to check what is going on. We can do this using the plotter tool, where we plot the amplitude over here 10 seconds. We can zoom in, and we identify that this oscillation is actually related to the 2 omega component that Jelena introduced. So we have to adjust the low-pass filter settings. We can do this here. So we increase the time constant. Now with a time constant of 15 milliseconds, now we can see that we get a very precise measurement. And now we're all set. Now we can start sweeping the gate voltages. So we do this in the sweeper tool. So we choose one of the auxiliary channels that we have connected to the gate and change the voltage from 0 to 1.5 volts. And then we can do this with 100 data points. And we are recording the amplitude of the current. Now you can see the device is in the off state. And then at some point, the current starts to flow through the device with the expected behavior. So now we would be all set to start looking for the quantum dot levels down here in that region close to pinch off. But unfortunately, we don't have a low temperature setup in our lab. So this demo was done just using a dummy transistor. And we will end here. Right. So let's think about the measurement speed in a bit more detail. So you've seen how important it is to adjust the time constant for the low-pass filter in order to get a precise measurement. And so if you want to record a map, such as these Coulomb diamond stability diagrams with, let's say, 100 times 100 pixels, every measurement will take you something on the order of 15 minutes. And now these quantum dot devices, they typically not only have one gate that you can adjust, but there are several gates. Maybe you want to control an external magnetic field. So you're entering a multidimensional parameter space, and essentially it takes a long time to characterize a single quantum dot device completely. And at this point now, an alternative approach becomes interesting, and this is the RF reflectometry. So how does this work? Now we work with high frequency signals. So we apply an RF wave on the order of, let's say, hundreds of megahertz. And then we don't measure the current through the device, but rather the amplitude and phase of the signal that gets reflected. How does this work? So typically, so you have the cables that are attached to your device. This could be this Z0 here. Of 50 ohms, and then you have your quantum dot device that has a different impedance. And now if you have an RF signal that encounters such a change of impedance, part of the signal will be back reflected. And in particular, the back reflected amplitude and phase depends on the change of impedance here at this interface. So this actually allows us to, by looking at the back reflected wave, to get an idea of the impedance of your device. Now, why is this interesting? Well, there's several reasons. First of all, we can now use much higher frequencies, so on the order of hundreds of megahertz, that allows us to get away from like low frequency noise sources, such as the 1/f noise. And then secondly, it of course allows us to measure with much smaller time constants, so we can increase the measurement speed, and in fact we can get a full map, such as a Coulomb diamond stability diagram, in just a few seconds. Now let's look at the setup in a bit more detail. As a first step, if you want to do such a measurement, you have to attach a tank circuit to your quantum dot device in order to get an impedance of that entire resonance circuit of approximately 50 ohms. So a simple schematic is shown here. Your quantum dot device here can be modeled as a resistance and a capacitance in parallel. And then you want to attach a tank circuit that in the simplest version consists of an inductance and a capacitance. And now you want to precisely measure the amplitude and the phase of an RF signal that gets reflected from the sample, and with frequencies on the order of hundreds of megahertz. And for this, the UHF-LI lock-in amplifier is actually a great tool. So you can create such a signal, use a directional coupler to put this signal onto the sample, and then measure the reflected part here using the signal input. And then to start your measurement, what you would do is first you find the resonance frequency of this resonance circuit. So to do this, you sweep the frequency and then measure the reflected amplitude and phase. And at the resonance, you're expecting to see this characteristic dip here in the amplitude. And now, after you've characterized this, you can choose a frequency here for your measurement that is somewhere here close to the resonance, and then start changing the quantum dot gates, magnetic fields, and so on to map out your device entirely. And now if the quantum dot state changes, for example, when it becomes possible for an electron to tunnel in and out of the quantum dot, that will change the impedance of your entire resonance circuit here, and you will be able to observe this as a change in reflected signal. Here's another quick demo, this time of the UHF-LI lock-in amplifier that goes up to 600 megahertz. We start by creating a test signal of 100 millivolts and apply this to our, in this case, it's quartz resonator. And then we can use the sweeper tool. In this case, we monitor the reflected amplitude and phase. And we sweep the frequency from 222 megahertz to 226 megahertz, because I know that the resonance is in that kind of regime. We do this with 100 data points. Now we can identify that the resonance is around here. We can zoom in and do another measurement to get a couple more data points. And yeah, so this allows us to nicely and very quickly characterize such a resonance circuit. And now we would be all set to start measuring our quantum dot device. Finally, I want to show a real example of such a measurement. So this is kindly provided to us by Brian Willis from UCL. And so this is here based on a carbon nanotube where a double quantum dot has been defined. And here you can see an example of the measurement. So this is the reflected amplitude here as a function of two voltages. And in the reflected characteristics. And with this, I would like to summarize the second part of this webinar. I have given a quick introduction to quantum dots and explained why interfaces are so important for these devices. And then I've introduced two techniques how to measure quantum dot devices. In particular, I've introduced low frequency transport measurements and I have shown how to set up an RF reflectometry measurement. Both of these techniques obviously have their own advantages. For the RF reflectometry, it is clearly the high measurement speed that allows you to get like a full map in just a few seconds. And in addition, it is even possible to do parallel measurements of several quantum dot devices using just one signal line if they're on the same chip. Yeah, now we come to the second part of the Q&A, and I'm looking forward to your question. If you haven't done that already, you can type them into the question box now.
Thanks so much, Heidi. Thanks for this really nice presentation on quantum dot transport and RF reflectometry. Let's now see, as Heidi mentioned, please keep your questions coming. We already have some in the queue, so why don't we get started with you, Heidi? So there was one question. What is the fastest speed of the RF reflectometry? What can you achieve?
Yeah, that's a good question. So there's basically two limitations. I mean, first you have to think about your measurement instrument, but then also about the rest of your setup, right? And so for your measurement instrument, in case of the UHFLI, the smallest time constant is 30 nanoseconds. So that means you could, in principle, get a data point in like 100 nanoseconds. But typically there are, bigger limitations from other components in your setup. So more realistically, you would look at like a microsecond or so for a data point.
Okay. There is another question about using the RF reflectometry. How is it possible to characterize several quantum dots in parallel, and what are the limitations there?
Yeah, sorry, I kind of cut this short at the end of my presentation. Thanks for asking. Yeah, so the cool trick there is that with the UHFLI, you can do a frequency multiplexing. So you can have one signal generated that consists of several frequencies, and you can demodulate at these different frequencies at the same time, at actually up to 8 frequencies. And then obviously you need to be able to distinguish your quantum dot devices, but this you can do by building tag circuits with different resonance frequencies. And so then each quantum dot will actually only respond to one of the frequencies. And you asked about the limitation. There's actually no limitation in terms of frequency, so you can run these 8 signals at the full frequency up to 600 megahertz.
600 megahertz. Okay. Thanks a lot, Heidi. There is a question, so keep the questions coming. So there's a question about data acquisition. So how is the data acquired? And is it possible to use Q codes for this?
Yeah, I'll start with the second part of the question. Yes, it is possible to measure with Q codes. We provide drivers for Q codes in Labra, for example. So that's one option. In general, you have different alternatives to acquire the data with the lock-in amplifiers. You can either use the built-in user interface that I've shown you now in the demos. But often, of course, you would want to automate your measurement, and you can do this by using the APIs, which we provide for different languages. So you can do Python or MATLAB or LabVIEW, whatever you want, and then just interface with the device and basically pull out the data for your own measurement routine.
Okay. Thanks a lot. Let me just look into several questions that came for me. So there was one question on the current or voltage preamp for the lock-in. Yes, of course. I mean, these preamps are regularly used, definitely for low temperature measurements. These preamps are placed very close to the chip, so it's a cold preamp. But there are many preamps commercially available that you can use, and you'll be able then to get better signal-to-noise ratio in this case.
But maybe we can add there that it's not an absolute requirement to use a preamplifier, right? The instruments also have several range settings. So if you use the smallest range, you can get very precise measurements already with the instruments without any preamplifiers.
Exactly. Thanks, Heidi. And there was another question. I think I can connect these two for you and myself. So you have shown a frequency sweep for the resonator, and there was also a question about sweeping the DC bias for DI/DV measurements that I showed. Maybe we can have a few comments on that. You want to do it, or shall I go?
I can quickly answer. Whatever you prefer. Yeah, absolutely. You can sweep the DC bias voltage. I've quickly shown that we can generate a test signal that consists of a DC voltage component and an AC component. And the way this is done is that you essentially create a DC voltage with the MFLI that is then added on top of your modulated signal, and then you can just sweep this DC bias voltage as you wish. You could use the sweeper to do this, for example. And obviously this is required if you want to map out these Coulomb diamond diagrams where you have the DC bias on the y-axis.
Yeah, there's also mention of speed over here for DI/DV measurements. Maybe just to add on top of that, right? So depending on how good is or bad signal to noise, right? What will ultimately determine the speed of the sweep is the how much noise you have. So if you have a lot of noise in your system, then you really have to reduce the filter bandwidth or increase the time constant. And then you have to wait about 5 to 10 time constants in order for the signal to settle, because you're moving the bias voltage, and this will basically determine your DC bias sweep and frequency sweep as well. In any case, you kind of have to synchronize your filter settling time and the speed. And actually this is done automatically within the sweeper that Heidi just mentioned.
But you can of course also control it for yourself if you
exactly.
choose different values. So
exactly, we have several settings. Exactly. Okay, so there are a couple of questions about a second order correlation function and some sort of maybe more advanced and even simulation questions. So just to clarify, in principle, things like second order correlation function is something that you would have to do in the API, and that's what Heidi has been doing. Some of these videos, these are actual measurements. And of course, we know theoretically what these Coulomb diamonds should look like. So these were not simulations, but are drawings of the stability diagram. Okay, I think we have time for a few more questions. There is one question that's very easy to answer. Are these lock-in amplifiers commercially available? Yes, they are, as we've shown. These are you can get these lock-ins. You can either get in touch with us or go to our webpage. We'll be happy to talk about them. Another interesting question for Heidi. Is it possible to apply pulses to these signals that you send via lock-in amplifier? I guess it's the question for UHF-LI.
Yeah, I guess this question is then related to a more evolved qubit characterization or so, where you want to apply individual pulses and so on. And yeah, this is indeed possible with the UHF-LI, with our high frequency lock-in amplifier. There is an option of having an integrated arbitrary waveform generator where you can essentially then shape your signal as you want to meet the requirements of your measurement.
Okay, maybe just one more question. It's about the stability diagram. Do I need to program the instrument to provide me with the data? So I guess it's more in-depth question about how the data is acquired.
Should I take this?
I guess, yeah, I think that the AQ module could be.
Yeah, exactly. So we provide a kind of measurement module that I didn't show today. It's called the data acquisition module for obvious reasons, yeah, where you can essentially configure the instrument such that it records, the different sweeps here and puts them then together and to give a full two-dimensional image of the measurement. So this is one option, but alternatively, you can have your external measurement routine, for example, in Python, where you have loops or you use Q codes that was mentioned before to set up these sweep routines and then just collect the data and then plot it in these rows and columns to get the 2D diagram.
Thank you, and maybe we can slowly move to the a question for you, Heidi. So what is the biggest application for the RF reflectometry at the moment? There were a couple of choices here, but maybe you can tell us a little bit more about that.
Yeah, so I guess the qubit characterization is certainly a very big field at the moment. I mean, there's many people that would like to design new materials to benchmark their qubits and so on. And so if you're looking at a chip that has maybe not so many yet, but in the future, hopefully, thousands of quantum dots that would be your qubit, you want to characterize them very fast. And so this is certainly a very big field for the RF reflectometry.
Thanks, Heidi. And there is one last question for let's then close it afterwards. So there's a question if we can measure the second derivative of the conductance, so di squared over dv squared. So yes, the answer is yes. With the MD option that our lock-ins have, you can measure both first and second derivatives, so you can measure the inelastic processes in these systems. Okay, well, thank you so much for for all the questions. Thank you for attending the webinar. It was a real pleasure for Heidi and myself to be a part of it. And we'd like to say goodbye and visit us again for the next webinar.
Yeah, thanks for joining, and yeah, get in touch if you have any additional questions. Bye-bye.
Thank you. Bye.